Welcome. The Passive Sampling Technology Update team is proud to present an overview of the Polymeric sampling devices. This quick video will provide a high-level overview of the device, as well as instructions on how to use, deploy, and retrieve the devices. For more information on these and other passive sampling technologies, please visit the Passive Sampling Technology Update Guidance document. Polymeric sampling devices are diffusion-based equilibrium-type passive samplers. This training video focuses on the low-density polyethylene, or LDPE film, and solid-phase microextraction, or SPME fiber device coated with polydimethylsiloxane, or PDMS. The SPME technology employs glass fiber-coated PDMS, and these technologies are primarily used in the United States. These devices are used to sample a wide range of hydrophobic organic chemicals in groundwater, surface water, and pore water. They can also be used to sample indoor and outdoor air. Other polymeric sampling devices, such as polyoxymethylene or POM, have the same scientific basis and working mechanisms. Check out the ITRC Passive Sampling Web Guidance for more information on the POM sampler. During deployment, target chemicals and sampling media diffuse into the samplers and fully or partially reach equilibrium between the sampling media and the polymers. The samplers are extremely effective to achieve low detection limits for hydrophobic organic chemicals such as polycyclic aromatic hydrocarbons, or PAHs, polychlorinated biphenyls, or PCBs, DDT and its breakdown products, plus dioxin and furans. They are not effective for hydrophilic organic compounds and volatile organic compounds. The state of equilibrium can be estimated using performance reference compounds, or PRCs, which are often isotope-labeled target chemicals. The samplers are retrieved after a sufficient deployment duration, which can be influenced by sampling media, the surrounding environment, the sampling method, target chemicals, and polymer thickness. Polymeric sampling devices are commercially available to purchase from vendors, but they need to be cleaned, prepared with PRCs, constructed, and analyzed by a qualified laboratory. Now let's look at the components of the two types of polymeric sampling devices featured in this video. The SPME is a PDMS-coated glass fiber. The thickness of the PDMS polymer is generally 10 to 30 micrometers on glass fiber capillaries of various diameters. The cylindrical shape of SPME fiber is convenient for insertion into sediment directly, or with protection using stainless steel mesh or perforated protective metal casings. SPME fiber can be easily snapped after gently scratching using a ceramic cutter to adjust their lengths to meet detection limit requirements and to achieve the desired vertical resolution. Since SPME fiber can be very sharp, you must wear appropriate personal protective equipment when handling. LDPE samplers are typically configured in thin bulk sheets that are 25 to 100 micrometers thick. Since the LDPE sheets can float on water, the sampler should be enclosed in stainless steel sleeves or placed in a protective pouch for deployment. Before deployment, the polymeric sampling devices need to be washed with organic solvents to remove background contaminants. After cleaning, the samplers will be spiked with PRCs. PRCs must be chemicals that are not present in sampling media and will not interfere the analysis of surrogates and internal standards at an analytical lab. After PRC spiking, the polymeric sampling devices are loaded onto or enclosed into protective mesh or perforated protective casings for deployment. When ready for in-situ deployment, samplers need to be stored in a shield bag and kept on ice in a cooler to the project site. At the site, open a sealed bag of the sampler fan. Carefully place the sampler into target sampling media at a desired location and depth. A deployment consideration specifically for sediment pore water. The polymeric sampling devices can be deployed ex situ. Sediment samples are collected from the site and shipped to a laboratory. The samplers are deployed in sediment at the laboratory under controlled conditions to accelerate chemical uptake kinetics. Ex situ measurement results can also be compared with in situ measurement results. Ex situ measurement can save cost and time to obtain results, but it cannot account for the effects of field-related processes, such as groundwater upwelling, influence of surface water, or other environmental factors. After an appropriate deployment duration, gently retrieve the sampler from the sampling media. Any residue or solid buildup on the sampler during deployment should be removed with analyte-free reagent water and wiped clean. The retrieved samplers are immediately transferred into clean bottles and shipped on ice for analysis. The sampler masses need to be measured and recorded prior to shipment to calculate concentrations in sampling media. For aqueous media, freely dissolved concentration can be calculated using the fraction of equilibrium calculated from the analysis of PRCs. The fraction of equilibrium is applied as a correction factor. Different mathematical models need to be applied to fit the PRC data to predict the fraction of equilibrium depending on sampling media and deployment approaches. Some important takeaways about the polymeric samplers are: these devices measure the freely dissolved concentrations, which is essentially bioavailable and directly linked to chemical exposure. The samplers also measure time-averaged concentrations during deployment. When sampling for hydrophobic organic compounds such as PCBs, the device needs to be deployed for an extended period of time. It can take about 2 months to achieve a sufficient fraction of equilibrium. Non-aqueous phase liquids, or NAPL, can coat on the polymeric sampling devices, which can result in biased results. After retrieval, the samplers need to be carefully assessed for color change and smell to determine if NAPL is present. For more information on polymeric samplers and other passive sampling technologies, check out the ITRC Passive Sampling Update web guidance.